guys, you're welcome to today's class. I want to believe we are doing very fine today. I want us to pay maximum attention to today's class. I want us to pay maximum attention to today's class. It's going to be very interesting. It's going to be, informative, and it's going to be very much educative, like we have always done. But I want us to pay maximum attention to today's class because we are going to be talking about the calculation on half-life. So we are going to be talking about calculation on half-life. So we are still on. So let me say today's topic is radioactivity, or let me just say radioactive isotopes or decay. Let me say today's class is radioactive isotopes and half-life. I want us to pay maximum attention. If you are doing JAMB, move very close. If you are doing WAEC, move very close because I'm going to be, explaining a whole lot of things here. I'm going to be explaining a whole lot of things. So take a seat and pay maximum attention to this very particular class because all the all the teachings today, all what I'm going to be revealing today are very informative, and I want us to get the full gist of today's class. So you're welcome once again. If you are just watching this YouTube channel for the very first time, kindly subscribe to this channel and turn on the notification bell so that when I upload any video, you are going to be notified. So pay maximum attention. Let me take you through what I have for you for today. Don't forget, in our last class, the previous class, I talked about radioactivity. I did a very wonderful job on giving us a very good background about radioactivity. If you have not watched that very particular video, go and watch it. So, but the basic thing we talked about in radioactivity, okay, in radioactivity basically is that we said it is the breaking down, okay, it is the breaking down of heavy nuclei. The breaking down of heavy nuclei. And when these nuclei break down, they can emit either alpha, okay, they can emit beta, they can emit gamma, or emit two of these three. We have talked about all these. We have talked about their two. I want to believe you are still together. We have talked about their characteristics. So for the fact that this nuclei break down and they emit radiation, then we said they undergo radioactive decay. Yeah. So for the fact that this very particular, because we have learned the introduction to radioactivity, and we have talked about even the radioisotopes, we have talked about that. So for the fact that this very particular nuclei break down, okay, and they emit radiations for them to be stable, we said they have undergo radioactive decay. I want to believe we are here. That means they have undergo what we call radioactive decay. So we are going to be looking at this mathematically. I'm simplify it. Okay, I'm going to take my time to simplify it so that we understand. So if you are not that good in mathematics, just pay maximum attention because I'm still going to show you a more simplified way of solving this thing so that it will be faster, interesting, and you'll get it once and for all. So I said for the fact that all these heavy nuclei break down, okay, and they emit radiation, then we say they undergo what we call radioactive decay. So let's talk about radioactive decay now. Let's talk about what radioactive decay. Now let me give an instance. Let's take, for example, I have a nuclei like this, just an example. Just take, for example, I have a nuclei like that. This nuclei at time t, before it started breaking down, we have it to be n naught. N naught means the initial mass before it started breaking down. Okay, let's say, for example, at a particular time, it now broke down to this. that broke down to something like this. Just an example. Now, so don't forget that this nuclei is breaking down to give us this. So that means at a particular time t, it would have break down to this and would have become another mass with respect to this time. I don't know if this is clear. This is a particular nuclei. I'm using it as an example. That is the initial, this N naught is the initial, mass, or is the initial nuclei before it started breaking down. And that's at time equal to 0 before it started breaking down. So at t equal to a particular time, it has broken down to n in respect to t, meaning I am going to have a new mass now with respect to this t because it has actually broken down. I don't know if that is clear. So this law states that, so I'm talking about radioactive decay now. The law states that, the law states that, okay, the law states that the number of radioactive nuclei, the number of radioactive nuclei decaying per unit time, okay, decaying per unit time is directly proportional. I will explain. That's why I say you need to take your time to listen to this video, pay maximum attention so that you will understand what I'm trying to say here. Is directly proportional to the number of nuclei present at that instant. What am I trying to say here? The law is saying that our change, okay, our change in this, the law is saying that what the law is saying mathematically, I'll take my time to explain, just pay maximum attention. The law is saying that our dn, okay, over dt is directly proportional to n. What do I mean by dn over dt? My dn over dt is simply my decay rate, okay? It's simply my decay rate. And my n is number of particles. I want to believe this is clear. My n, which means that if this n, if the number of particles is bigger, it means that the decay rate too will be larger. Can you see that? That's what that law is saying, which means that the number of particles is directly proportional to the decay rate. So if the number of particles is smaller, it means that the decay rate too will be smaller. Okay? If my dn dt is smaller, it means that the number of particles is smaller also. While if my dn dt is bigger, it means that what my number of particles is bigger. So my dn over dt is directly proportional to my what? Introducing our constant here. Introducing our constant. And our constant is what? Is lambda. Okay? Like our normal variation, we are going to have dn, okay, over dt, right, is equal to minus lambda n. Now you'll be surprised. How come do I have minus? This minus is telling me that as this very particular n is decaying, is getting smaller. That's why this minus is here. Okay, because if this minus is not here, if n is still positive, it means that as n is decaying, n is still getting bigger, which is wrong. So the reason why I have to add my minus here is to tell me that as n is decaying, okay, it is getting smaller, it is reducing. That's why I put my minus. Why this lambda is just like my normal constant. I want to believe this is clear. So from here, if I have my dn over dt is equal to minus lambda, I cannot have rearranging this or making minus dn go to one side. I don't know if you dn go to one side. So I want to bring dt to this place, then n to this place. So I can have dn, okay, over n. I want to believe that's the n over n is equal to minus lambda dt. Can you see that? So it's just like I'm making subject of formula and I want minus lambda dt to be here. So at the end of the day, I'm going to have the n over n is equal to minus lambda dt. Right? If we integrate both sides, if we integrate this expression, just pay maximum attention. The reason why I'm doing this is because of some students that are in 100 level, you might be asked to do this in school. Okay? You might be asked to do this in school. My fellow colleagues too, that are chemistry instructors, actually need this too. That's how I'm doing it. So pay maximum attention now. So if I integrate this, I will have my integral of what? Dn over n, right, is equal to integral of what? Lambda dt. So what is the limit? Let's go back. What is the limit? Look at this. Look at this place. My n naught, the limit here is that I have my n naught to my t naught, that's time. Then I have my n dt to my t. So that's the limit. So I can go down and say, okay, the limit is that here is the limit is from n naught, okay, to n, right? Then I have my from time t, which is 0 towards to t. So because if you look at this integral, you see this is talking about the t and this is talking about the n. So my n naught is the initial amount. So the integral is the n naught, which is the initial amount, breaking down to n, which is the final amount after breaking down, starting from t naught to a time t. I want to believe this is very, very clear. So from here, what do we have? To take the integral of this side, we are going to have that our ln, okay, our ln to be n over n naught. Don't forget that's the limit. N over n naught is equal to exponential minus, sorry, you know, the minus is here. Let me still put it. You know, for this very particular integral, this minus is still here. Okay, this is the minus. So exponential, the minus lambda, what? Lambda t. That's what we are going to have. And if we are rearranging this, we are going to have that. If we rearrange this, we are going to have that our n over n naught, okay, is equal to exponential minus raised to power minus lambda t. I want to believe this is clear. So if we are rearranging this, if we rearrange this, we are going to have that n is equal to n naught, okay, exponential raised to power minus lambda t. Please take note of this. So which means the first thing I need to note is that I have that my n is equal to n naught exponential raised to power minus lambda t. Please note this. Very, very important. This is a general one, and that's how this very particular law is gotten. Please pay maximum attention to this. Pay maximum attention to this. So if I want to calculate anything on, you know, my radioactive decay, I can actually use this. Though I'm still going to give you a simpler one. I'm just doing this for some of us that are A-level students, you know, they actually need this. So where our n, let's take where our n now. What is our n? Our n is the number of the atom undecayed, right? Number of atom, let me say remaining, so that you will understand that. So after a particular amount of decay, the amount remaining is the n. Why the n naught is the initial amount present before it started decaying. Okay? Initial amount present. I want to believe we are still together. Why our t is what? Is our instant of time. instance of time. I want to believe you are here. Okay, so take note of this, guys. Take note of this. I'm going to show us some interesting stuffs here. So take note of this. N is equal to n naught exponential h power minus lambda t. Take note of this formula. Very, very important. Now, let us get another expression for half-life. Let's get another expression for half-life. Let's get for half-life. Half-life. Okay. Half-life is represented by T half. And what is half-life? The half-life of a radioactive element, the half-life of a radioactive element is the time taken for half of the atoms, let me put it that way, atoms initially present in an element to decay. So when you talk about half-life, you are talking about the time taken for half of the atoms initially present in an element to decay. What do you mean by that? Let's take, for example, this is an element, the initial amount was 10 grams. The time taken for this element to decay from 10 grams to half of 10, which is 5 grams, is what we refer to as the half-life. I want to believe this one is very, very clear. So the time taken for it to decay to half of the original amount. So the time taken for 5 to decay to 2.5 grams is what we still refer to as what as our half-life. I want to believe this is clear. So let's get an expression for half-life. Expression. So for half-life now, okay, we know N is our initial, N is the number of atom that is actually remaining. Okay, and that will be what? That will be our N naught over 2. Do you see that? That's our N naught. N naught is the initial amount. So it's just like I have this 10 gram. Okay, 10 gram is the N naught over 2 will give me N. Do you see that now? So N naught is the 10. That's what I started with. When this thing decay to half of its original amount, that will be divided by 2. That will be 5 gram, which will give me N. So my N is equal to N naught over 2. So let's put this in this equation that we first of all derive. This very particular equation, let me write it out. That's N equals to N naught exponential raised power minus exponential minus lambda t. You see that now? So let's insert this N, which is N naught over 2. So anywhere we see N here, we put over 2, right? So let's go now. We have, this is N, so we substitute now for this. We say N naught over 2 is equal to N naught exponential minus lambda t. I want to believe this is clear. Okay, so from here, we can cancel out N and N naught. So if we cancel out N naught here, we are going to have 1 over 2 is equal to x minus lambda t, because this, we already cancelled this. So we are going to have this expression. We are actually following. So from here, the natural logarithm, we take the natural logarithm. Natural logarithm is the ln on your calculator. Logarithm of both sides, you are going to have ln 1 over 2, okay, is equal to, if we take the ln we cancel out this exponential. Cancel out this exponential, it now become minus lambda t. I want to believe this is clear. So from here now, our laws of logarithm, let's do small mathematics here. Our laws of logarithm, one of the law is saying that if I have log 10 times log 10 of 20 times log this to 5, the same thing as saying log 20 plus, I have plus, so I can say log 20 times 5. Do you see that? So if I have log this 20, okay, divide, or let me say minus log 10 5. It's still the same thing. If it is this is minus, so minus, so it's still the same thing as saying log 10 20 divide 5. You get that now? So if it is like this, I can change it to this subtraction. So if you look at this ln 1/2 is in the division sign, so I can change it back. If it is like this, it means that it is in the subtraction form before they now brought it like this. So I can expand this now. If I expand this, what am I going to be having? So my ln 1/2 is the same thing as saying ln 1 minus ln 2. Do you see that now? Because the law of logarithm means that if you have the same log, okay, the same log, and it is subtraction, you can divide. So if you have it as division, you can bring it back to this. So on our calculator, if let me punch my ln 1, that's giving me 0, which means this will be equal to, our ln 1 is giving me 0. Can I see that now? Minus, let me punch my ln 2. Ln 2 is giving me 0.6. So it's giving me 0.693. I want to believe. So we have resolved the whole of this. Ln 1/2. So ln 1/2, if we subtract this is going to give us minus 0.693. We have sorted this, which is that ln 1/2. So from there, what are we going to have? So from here now, here, you can now have that. Our ln 1/2 is what? Is 0.693, right? Is equal to our minus, right? Lambda what? T. You get that now? So minus can cancel minus here. Minus cancel minus here, and we are making T the subject of formula, which is our T half now. Don't forget, which is our half-life. So we can now have, making this the subject, you can have our T half to be equal to what? 0.693 over what? Lambda. Can you see that? Please take note of this. I've derived two formulas now. Very, very important. I've derived two formulas now. And the first one is that we have that our n is equal to n naught exponential minus lambda t, while the second one is our t half is equal to 0.693 over what? Lambda. Some people use this lambda as k. It's still the same thing. It's constant. It's either you say lambda or k. So take note of this. I want to believe you are still following. So if you are doing jam, now listen now. If you are taking jam, you are concerned with these formulas. Okay, you are concerned with these formulas. Very important. So take note. Let me write this now. Take note for Jambite. You might not really understand those proving. I'm just doing that for A-level students. But if you are taking jam, what should you pay attention to? Pay attention to this formula. And what is the formula? N is equal to n naught, okay, exponential minus lambda t. Or this is the one I love using, which I always advise my students to. If you don't know this one. A is equal to a naught, open a bracket, half, close the bracket, then t over h. These two things is meaning the same thing. This and this is the same, and I'll be using the two of them to solve some questions for you so that you see. So I always advise Jambite that If this is too clumsy for you, this is better. So take note of this, very important. Or, and sorry, not even or now. And this very particular one, T half equals 0.693 over lambda or K. You get that? So this and this is meaning the same thing, but I see this to be, a bit better than this because of the exponential and all the rest. So you can still say A equal to A naught, open a bracket, half, close the bracket, then raise to power T over A, where your T is the time and your H, where your T here is the time and your H here is the half life. So your A is still saying the what? The amount that is remaining, while your A naught is the initial amount. So if you are taking jam, please take note of these two formulas. I've said that this formula and this formula is the same, but I prefer this one more, and you see that to solve a whole lot of questions. So take note of these formulas. Now let's see some examples now. Let's see some examples. How can we apply these formulas? Examples. Let's see some examples. How can we apply this very particular formula? This formula to solve equation. Let's take equation. Example 1 now. They said the equation C12H22O11 plus H2O is giving C6H12O6 plus C6H12O6 shows the hydrolysis, okay, of sucrose using excess water. Calculate the half-life of the reaction if the decay constant for this reaction is 6.10 10 raised to power minus 5 per seconds. This one is a very simple question. And that's the reason why if you are taking JAMB, you have to be very careful. Read the question very well. Know what they asked you to do. What did they ask us to do? They asked us to look for what? The half-life. And they asked us to look for the half-life. They have given us the decay constant in the question. Can you see that? They have given us the decay constant in the question. So what do we do from here? We say that we don't know. But here they are giving us the decay constant. Look at that from the question. They said the decay constant. So our K or our lambda, anyone you want to use, you are correct. So our K or lambda, anyone is correct. 6.10 times 10 raised to power minus 5 per seconds. Now, since we are asked to look for our what? Our half-life, then we know that our T half is equal to 0.693 over what? Over K or lambda. So from here, we have 0.693 over what's our K, which is our constant, 6.10 times 10 raised to power minus 5. So if we use our calculator, our T half is going to be, let me use my calculator. Our T half is going to be, okay, 0.693 divide this, okay. My calculator, I have 1.136 times 10 raised to power 4 seconds because it is time. So anytime you are asked to look for your half-life and you are giving your decay constant, it's a direct question. Or you are giving your half-life and you are asked to look for your constant, it's still the same thing. If you are giving the value for this and you know this, you can look for your K. You see that? So that is that. Very, very simple. So when they ask you to look for your half-life, given your decay constant, you can actually use this to look for it. So very, very important. Now let's go to another question. Don't forget, I told you something. I said this very particular formula, if you are not forgetting, I said this very particular formula is our n is equal to n naught exponential minus, lambda t, is also the same as the one I told you to, that I said I prefer, which is a is equal to a naught half t over h. So now pay attention to this. I'm going to use the 2 to solve this very pay maximum attention to this. Okay, so look at this question, and I'll teach you. So if you are a jam student now, if you are a jam then listen to this. If you are a jam listen to this, because I'm going to show you something in pay maximum is now. Now look at this question. Example 2. It's a jam question, and I want to show you a lot of ways that you can solve this. They said the half-life. They said the half-life of a radioactive, so pay maximum attention, guys. A radioactive substance is 14 days. Is 14 days. Okay. If 48 grams of this substance, if 48 grams of this substance is stored, okay, after is stored, after how many days? After how many days will 1.5 gram of the original substance remain? So calm down, guys. A simple question. Just calm down. Original substance remain. So I'm going to address everybody here now. A, they said 84 days. B, they said 70 days. C, they said 56 days. And D, they said 40 days. Now pay maximum attention to this. If you are writing WAEC, let me start from there. If you are writing WAEC, let's take for example, this is a theory question. You are writing WAEC. This is a theory question. You are meant to go the normal way you're supposed to solve it, because they're not going to give you option if it is a theory question. So let's solve like we are writing WAEC first. Then I will now attempt to jump by to tell you the fastest way to solve this question. So let's go like we are writing WAEC now first. Solution. How do we go about this? They said the half-life of a radioactive substance. So let's take the half-life is what? Is 14 days. Is 14 days. Okay? The half-life is 14 days. They now said if 48 grams of the substance is stored, meaning the amount we started with. Can you see that? The amount we started with, which is our N naught, initial amount we started with was what? Was 48 grams. I want to believe we are still here. The amount we started with was actually 48 grams. You get that now? Was 48 grams. They now say, after how many days will 1.5 gram of the original substance remain? After how many days will 1.5 gram, which means after we started with 48 grams, the amount that was remaining, do you get that? After how many days will 1.5 gram of the original substance remain? So the amount that is remaining, N, is 1.5 gram. They now said, after how many days? So what we are looking for now is time. After how many days? I want to believe you are still here. Okay, so let's go now. Let's solve using this now. We have that our N, we have that our N we have that our N, Okay, our n is equal to n naught exponential minus the t. Remember, so what is our n now? We have gotten our n to be 1.5 equals to our n naught is what? Is 48. Here, exponential our what? Minus lambda. Now, let's get our lambda. Okay, let's get our lambda because we know that our T half is equal to 0.693 over what? Over lambda. And we are given our half-life already. That's T half. What is the half-life in the question? It is given already 14 days. Can you see? So I can have 14 is equal to 0.693 over what? Over lambda, right? So our lambda will be 0.693, okay, over 14. So our lambda here, calculator is 0.693 divided 14. That's giving me 0.0495. I see that now. So we have that our 1.5 is equal to 48 exponential minus 0.495 t. I want to believe that together. So we want to make t the subject of formula over here. What do we do? Let's eradicate 48. So let's divide both sides by 48. So we are going to have this divide 48, this divide 48. So this will cancel this. I want to believe you are still with me. So 1.5 divided is giving me 0.03125, okay, which is now equal to what? Exponential minus 0.495 t. I want to believe this is clear. So from here, what do? We want to eradicate the exponential now. So what do? We take ln on both sides. So taking ln, that's natural log of both sides, I'm going to have ln 0.03125, okay, is equal to, so the ln will cancel out this exponential, minus 0.495 t. So from your calculator, just press ln is 0.03125, not log. You press ln. Your ln is your natural log. Ln, you see it on your calculator. Okay, so let me use my calculator here. Ln is 0.03125. That's giving me minus 3.465735903. That's what it's giving me. Minus 3.65735903. They will now be equal to minus 0.495 t. So what do? Minus can cancel minus. Okay, so our t will now be what? Will be 3.465735903 divided by 0.495. 0. Sorry, 0.0. Oh, I'm seeing a mistake. I just saw 0.0. So this is 0.0. There's an omission here because this is the lambda. 0.0495. 0.0495. So let's see what our t is going to give us. 0.495. So 3.465. Let me use my calculator. Wow, I'm getting t to be 70 days. Can you use a calculator too? Can you see that? So the answer here is what? Is B. Okay, now using this, I told you, I said anyone will still give us. So if you are writing WAEC, this is how you are meant to solve it. Because if you are doing JAMB, you cannot solve it like this because you are not giving a calculator that has all this link. You are not giving. Can you see that you are not giving? So you are not giving a calculator that have all this. So that's why I'm going to show you how to solve questions like this if you are a JAMB. So, but if you are WAEC, you are writing WAEC, you are preparing for WAEC, you're a WAEC student, then you are meant to solve it like this to get your full mark. Now, I still said we can use this very particular formula too. Let me do it here. I said we can use our A is equal to A naught, anyone you are comfortable with, half T over H. Okay, so our A, same thing with this. Our A here is the amount that is remaining, right? The amount that is remaining is our A. While our A naught is the initial amount we started with, which is this the same thing. So our A, the amount remaining is 1.5 is equal to our A naught. What is our A naught? That's the amount we started with. That's 48. Then we have 1 over 2. We are looking for time, right? That will be T over what is our half-life? 14. Can you see? So from here, what do we do? From here, so we divide both sides by 48, like we did there. So if we divide both sides by 48, we are still going to have, let me go down a bit. So if we divide both sides by 48, we are going to have what? This divide 48, this divide 48. So this we cancel this. So 1.5 divide 48 is going to give us 0.03125, right? Is equal to half T over H. This one is short. I can see you are not seeing the exponential here again. Can you see? So here now, what do? I will take log of both sides. So if you are using this, you are taking log of both sides. If you are using this, you are taking ln. So if you are using this one, you are taking log of both sides. If you are using this, you are taking the ln because of the exponential. But the exponential is not here now. So we take log of both sides. We are going to have log to base of 10, 0.03125. Then we have equal to log again to base of 10, half T over what is our H? That's half-life. That's what? 14. I want to believe we are together. Now remember that law of log, when you have log 10 to base of 10, right? Raised to power 2 is the same thing as saying 2 log 10, 10. So I want to apply that here. So let me look for log 10. Log of 0.031 log 0.031. That's giving me minus 1.50514. Let me say 15 because it's 149. So let me say 15 is equal to, I'll bring this to the back of log using this very particular law of logarithm. So we have T over 14 times log 1 over 2. You see that now? So from here, what will I have? I will have that minus 1.50515 is equal to T over 14 times log of half. That's giving me minus 0.30103. You see that now? So from here, what do we do? Minus can cancel minus, so that will be safe. And from there, we cannot have what? We cannot have 1.50515 times 14 now be equal to 0.30103 T. So we divide both sides by that. So let's see. 1.50515 times 14, okay, divide 0.30103, and that's giving me approximately whole number 70 days. Can you see that? Interesting. So you can use any of the two formulas. I prefer the second one because exponential is not there. So it's just the number must take log of both sides, and we are okay with that. Guys, so if you are taking WIAC, you can solve using the first one. You can solve using the second one. Very, very important. But if you are taking JAMB, look at that question. You are taking JAMB. How do we solve this question? You are taking JAMB. Now, for JAMB students, You know, you are not going to be using calculator, so there is no way you are going to get log 10 of this. There is no way you are going to get lean, right? So how do we solve this? How do we solve this? Are you ready? Okay, now let's look at this. How do we solve this? If you are taking jam, please take note of this formula. Take note of this formula. Stages of decay is equal to time taken over half-life. Take note of this formula. Stages of decay is equal to time taken over half-life. Guys, take note of this thing. Jambite, come closer, come closer. So stages of decay. Now let's go back to the question. What do I mean by stages of decay? Let's go back to the question. What do I mean by stages of decay? Now look at it. The element started from 48 gram, right? 48 gram, okay? And stopped at 1.5 gram. This was 48 gram, then 1.5. So the stuff, the element decayed from 48 gram to what? 1.5 gram. So let's go now to the stages of decay. Let's get our stages of decay now. What is our stages of decay? Now look at that. The element came from 48 to what? To 1.5. So let's see how many stages is the decay will occur, because we are talking about half-life. So 48 divided by 2. 48 divided by 2 is going to give me what? 24. That's the first decay. 24 divided by 2 is going to give me what? 12. Can I see that? Divide by 2 again. That will give me what? That will give me 6, right? Divide by 2 again. That will give me what? 3. Divide by 2 again. That will give me 1.5. Can you see? So the element came from 48 to what? To 1.5. So how many stages? This first stage, right? Year to year, second stage, from 12 to 6, third stage, from 6 to 3, fourth stage, from 3 to 1.5, the fifth stage. So the stages of decay is 5. Look at that. So stages of decay is what? Is 5, which is equal to, what did they ask us to look for? Time taken, right? Over half-life. And what is our half-life? That's 14. So our T is now going to be 14 times 5. And our T definitely is going to be what? 70 days. Fast. You get the point now? That is it. So guys, if you are taking jam, sharp, sharp, you are done. Sharp, sharp, you are done. So take your time. Stages of decay is equal to time taken over half-life. And with this, you are done. So if it is WAEC, you cannot solve this way. You need to just go through that way so that I can get your full mark. But jam, you are time, you are really, you are time limited. Okay, time is not on your side if you are writing jam. So you can just do this, you get your answer straight. I want to believe this is clear. I want to believe this is clear. To believe this is clear. So very, very important. That is just it, guys. Very, very important. Very, very important. So let's take another one. Let's take another one. This is jam. Now look at this. We use that our short method now. A radioactive substance. A radioactive substance of mass 768 gram has a half-life of 3 years. Of 3 years. After how many years? After how many years? This is a jam question. Does this substance, after how many years does this substance leave only 6 gram undecayed? ZA, A here is 21, B it said is 18, C it says 15, and D is 12. Don't forget all other formulas, we are treating this as JAMB question, so we can still use that to solve, those formula I gave, we can see that's our A naught exponential. But let's do this faster. JAMB students, now pay attention to this. After how many years? I told you that stages of decay is equal to what? Time taken over what? Over half-life. I believe this is clear. So let's go now. Don't forget that the substance started from 768 and what? And ended on 6 gram. So let's see how many stages it will take from 768 gram to what? To 6 gram. So let's go. 768 gram divided by 2. That's going to give us 354 gram, right? Divided by 2 again. That's going to give us 192 gram. Divided by 2 again. That's going to give us 96 gram. Divided by 2 again. That's going to give us 48 gram, right? 48 gram divided by 2 again. That's going to give us 24 gram. 24 gram divided by 2. That's going to give us 12 gram. 12 gram divided by 2. That's going to give us 6 gram. That's the stopping point. Let's see how many stages from here to here. 1, 2, 3, 4, 5, 6, and 7. So the stages of decay is 7 is equal to, what is the time taking? That's what we are looking for, over our half-life. They have given us in the question half-life of what? Of 3 years. So 3. So our T is going to be 3 times 7, which is what? 21 years. Look at it. Clean. Easily done. Easily done. Like easily done. Easily done. Easily done. Can you see that? So very, very important for JAMBite. If you know this formula, you are going to solve a lot of questions. So pay maximum attention. Let me just take one or two questions again and I'm done. Let me explain this. Now, take note. The question can come in fraction. Do you see that? The question can come in fraction. Two, very, very important. Instead of the question coming in mass, it can come in fraction, it can come in percent. So how do you do that? How do you solve that? Take for example, look at this one. They said the half-life of an element is 5 days. Of an element is 5 days. If we have 10 gram initially, okay, what fraction, look at that, what fraction is left after, 20 days? So take note, guys, the question can come in fraction, the question can come in percent. So how do we solve this? Now they said, what fraction is left after what? 20 days. Let us know the stages of decay. You can see I'm emphasizing on that formula. Very powerful. Stages of decay will be what? Our time taking over what? Over half life. So the stages of decay is now going to be, our stages of decay will be time taking, that's 20, is it? Over half-life, that's 5. So our stages of decay will be 4 decay. Right? So it's going to decay 4 times. They now said what fraction? They are not saying what mass. They are not interested in the mass. Now look at it. Let me explain this well. Let's take, for example, the question is what mass will be remaining after 20 days, right? It will now be, it is 4 decay. So which means that we are going to go from 10, 4 decay. So we are going to have 10 gram to what? To 5 gram, right? to 2.5 gram. Okay, then from 2.5, let's say divide by 2 again, 2.5 divided by 2. That's giving us 1.25 gram. Then 1.25 gram divided by 2 again is going to give us 0.625 gram. So 1, 2, 3, can see 4. So if they have asked what mass will be left after 20 days, the answer would have been 0.65 gram. But they are not asking for mass, they are asking for what fraction. So if we are solving in fraction, this is how it's going to look like. I have already know the stages of decay to be what? 4 decay. So I'm expressing in fraction. So in fraction means the first half-life is going to be half, okay, times another half, which is the second decay, times another half, which is the third decay, times another half, which is the fourth decay. So we are going to have 4 halves. So, and that is not going to give me what? 1 times 1 times 1 will give me 1 over 2 times 2 times 2, 2 times 2, 4, 4 times 2, 8, 8 times 2, what? 16. So 1 over 16. That will be the fraction that will be left after 20 days. So this is the mass left after 20 days. This is the fraction left after 20 days. It's still the same. So it's just like you are expressing your mass in fraction. So it will be 1 over 16. I don't know if you are getting that. It will be 1 over 15. So if it is in fraction, I know the number of decay. When I know the number of decay, I'll just say 1 over 2, that's the first decay. 1 over 2 times 1 over 2 second decay, times 1 over 2 third decay, times 1 over 2 fourth decay. And that's 1 over. Let's say, for example, the question is in percent. We already know the number of decay. If it's in percent, right? Percent means from 100, which is the initial amount, to what? To 50%. From 50% to 25%. Can you see that? From 25%, 25 divided by 2, that will be 12.5%. 12.5% divided by 2, that will be 6.25%. So 4 decay, right? So from here to here, 1, 2, 3, 4. So if they have asked me the question in percentage, it will be 6.25% is what is the one remaining. If they ask me in fraction, it will be 1.1 over 16 of the fraction that is remaining. If they ask me in mass, it will be 0.625 gram that is remaining. This is clear. Question. This will be the last question. Just take your time to, take your time to study this. They are simple questions. Try your hands on past questions. I've given you, a cheat that for Jambite, it will make it easier for you. So understand that this is the amount left. They can ask you amounts that have decayed. So when you know the amount that is left, subtract from the initial amount, you will know the amounts that have decayed. Do you get that? What am I trying to say in essence? Don't forget that this one we did, this is 0.625 is the amount remaining, right? They can ask you the amount decay. So don't get it wrong. This is 0.25 gram is the amount that is remaining after it has decayed from 10 gram. So this 0.625 is the amount remaining. So they can ask you what is the amount that have decayed. You just say 10 minus 0.625. You get your answer. So if they ask you what is the amount that have decayed, that will be 10 minus 0.625. And that's around 9 points. So this one is the amount remaining. The amount that has decayed is 9.375. This one this is the amount that has decayed. So for this fraction now, this is the fraction that is remaining. What is the fraction that have decayed? I can just do 1 because it's a fraction. O is 1 in mathematics minus 1 over 16. So this one will be over 1. 16. That will be 16 here. 16 times 1. 16 minus 1. That will be 15 over 16. So the amount that is remaining is 1 over 16. Okay. While the amount that have decayed is 15 over 16. Can you see? For percentage, the amount that is remaining in percentage is 6. I can just say 100 minus 6.25. That will give me 93.75. So the amount that have decayed is 93.75%, while the amount that is remaining. So if you know the amount that have decayed, you know the amount. If you know the amount that is remaining, you know the amount that has decayed. I want to believe this is clear. Let me take this last one. Then just take your time to solve questions on your own. This is the last example. So let me do this. They said the half-life of a radioactive element, the half-life of a radioactive element is 3 seconds. If there are 15,000 atoms at the beginning, calculate one, the decay constant, two, the number of atoms remaining, the number of atoms remaining after 6 seconds. And the third one, they said the fraction of atoms that decayed. Can you see? The fraction of atoms that decayed after 6 seconds. So that will be the last question. Let's get that done very fast now. Let me go up so that we'll see the question, then we can solve. Okay, so the solution now. They say we should look for the decay constant. We know that our decay constant is T half equals to 0.693 over what? Over K. And they have given us the half-life in the question to be 3. Our values to say 3, which is our half-life, is equal to 0.693 over K. So our K becomes 0.693 over 3. So our K becomes, we are going to have 0.231 per second. That's our decay constant. Very clear, right? Okay, let's move on. The number of atoms, look at that. The number of atoms remaining after 6 seconds. Do you see that? After 6 seconds. So let's get our stages of what? Of decay. And what's our stages of decay? Time taken over what? Over half-life. Right? Time taken over half-life. So what is our time taken in the question? Our time taken in the question is what? Is 6. Because they said the number of atoms remaining after 6 seconds. And our half-life is 3. So the stages of decay will be 6 over 3. That will be what? 2 decay. Right? So 2 is just going to just 2 decay. So how do we now get the number of atoms remaining? So let's go now. 2 decay. What was the atom we started with? Let's go back to the question. What was the atom we started with? 15,000. So it's going to experience 2 decays, right? So let's go now. 15,000. 15,000. When it decay first, it's going to give us 7,500. So 7,500, because it will undergo 2 decay. 7,500 divided by 2. That's giving us 3,750. 3,750. So this is the first decay, this is the second decay. So number 2 answer, the atom that will be remaining after 3 seconds will be 3,750 atoms. Can you see? So, and the next question now says what? Fraction of atom that decay after 6 seconds. So we are still having 2 decay. So let's go now. Fraction now. Fraction. So number 3. Let's first get the fraction remaining. So you will understand what I want to do. The fraction remaining after 2 decay. So what is the fraction remaining after 2 decay? That will be 1/2 times 1/2. And that will be what? 1/2 times 1/2. That will be what? 1/4. So 1/4 is the one that is remaining. So what we are now looking for is what? Is the fraction of the atom that has decayed. So this is the fraction of the atom that is remaining, 1/4. So to get fraction that decayed, okay? I said that for O, this is the fraction that is remaining. So which means the fraction we started with is O, which is 1, right? So that will be fraction that decay now will now be 1 minus the fraction that is remaining, 1/4 over 1. So let's do the math now. This will be 4, right? So this will be 4 minus 1. That will be 3. Very simple. So the that decayed. Can you see that now? Can you see the question? So you have to take your time to understand. So the fraction that decayed, okay, the fraction that decayed is what? Is 3/4. And if what they ask me is the fraction that remains, that one is what? 1/4. Correct. I want to believe this should be very, very clear. So what you need to do is, if it warrants you, if it warrants you to go over this video over and over again, how to do that, or just have to stop there. That's just the problem I just have with students. Some of us will just that all this. So you don't have to take your time to study all this. They are not magic. Me that I'm saying it is not magic. So you just have to take your time to continue studying it. Okay? So you just have to take your time. They are very simple. They are very simple. Let me just give you this just to try your hands on it. Just try your hands on it and tell me what the answer look like. You tell me what the answer is going to look like. Just simple question. So just do this like assignment. Just do this yourself. Very simple. It said a sample of uranium has a half-life of 4 days. What fraction of the sample, remains after 24 days? A, we have 1/8, B, 1/16, C, 1/32, D, 1/64, E, 1/128. So just try your hands on this. Do this. Just try this one. Try this one too. And tell me what the answer is. How much of 5.0 gram of polonium-210 whose half-life is 150 days remain after 45 days? So they started with 5 grams of polonium, the half-life is 150 days, and the time is what? 45 days, right? How much of 210 polonium whose half-life is 150 days, the half-life is 150 days, will remain after 45 days? So just try your hands on this, guys. Try your hands on this. I know it might be very technical, but just try your hands on this. How much of 5.0 gram of polonium whose half-life is 150 days remain after 45 days? So if you cannot use that stages, you know the formula to use, that long formula. You can use it for this one. So, but just tell me what the answer. So how much of 5.0 gram of 210 polonium, that's the mass number though, they're just giving us, whose half-life is 150 days remain after 45 days. So this is more for WAEC students, like for if you're writing WAEC, NECO, this one is for you. But if you're writing that, try this too so that you'll be sure you can go, maybe you need to explain to somebody or you need to teach somebody, you know how to use the long formula and this. So that is that for that, guys. I want to believe you have learned a lot from this very particular class. I want to believe you have learned a lot. Yes, I want to believe you have actually learned. So if you are just watching this YouTube channel for the very first time, kindly subscribe to this channel and turn on the notification bell so that you will not miss my weekly videos. For Jambites, I wish you good luck. Take your time to do this, lay your hands on past questions, do this over and over again, practice, and definitely you'll be perfect at doing it. So thank you for staying with me today. Till we meet again on this very particular YouTube channel called Chemistry Hangout. Stay chemically active. I love you guys. Thank you.